Hello and welcome to my talk. This is joint work with Jim Delgrande. Here we looked at the question of how to make the actions of artificial agents that operate in shared environments with humans subject to social norms and moral guidelines. That is to say, we want to integrate concepts and results from the area of Deontic logics, which has been traditionally concerned with reasoning about notions such as obligation, permission, and prohibition, with a popular formalism for reasoning about actions and change, namely the situation calculus. In particular, you want to be able to treat so-called contrary to duty scenarios, a well-known example due to Forrester, which we slightly adapted here for artificial agents. But in the case of a household robot, we want to instruct it to not touch a valuable antique vase. However, if for whatever reason it has to move the vase, it at least should do so gently. And when the robot then actually moves the vase, we want it to do it in the appropriate manner. Another popular example is due to Chisholm. You ought to go help your neighbor. If you go help your neighbor, you should tell them beforehand. And if you don't help your neighbor, you shouldn't tell them that you're coming. And you actually then don't go helping them. Probably the most well-researched system of Deontic logic is SDL, which is nothing else than the standard KD model logic. The basic idea is that accessible worlds represent ideal worlds, and obligatory is whatever is true in all the accessible worlds. The problem is that when encoding contrary to duty scenarios in SDL, where conditionals are represented by material implications, one either obtains inconsistencies or undesired dependencies between the different statements, and this is why these examples are traditionally referred to as paradoxes. It was soon recognized that one should rather use dyadic obligations that represent defeasible conditionals, such as the one seen here, tell is obligatory given help. And then instead of a simple binary distinction between ideal and non-ideal worlds, we get an ordering of worlds according to their degree of ideality. The question we looked at here is how we can do something similar but apply it to the actions of a situation calculus theory. Notice that we want to regard such statements as constraints that the agents need to take into consideration in addition to its overall task. So the situation calculus is a dialect of first-order logic for reasoning about actions and change. Terms come in three sorts: actions, situations, and objects. Situation terms are constructed using the constant S0, which stands for the initial situation, and the binary function doAs, which denotes the application of action A in situation S. Basically, you should think of situations as sequences of actions. Properties that change due to actions are represented using so-called fluent predicates and functions, which take a situation as the last argument. We then represent a dynamic domain using a so-called basic action theory consisting of several ingredients. First, we have an initial theory, which is a set of formulas uniform in S0, which means that S0 is the only situation term mentioned. Next, we use the successor state axioms for representing action effects, which relate the value of every fluent after the execution of an action to a formula talking about the predecessor situation. And here we ignore preconditions for the sake of simplicity. And finally, there's also a set of foundational axioms that make sure that situations form a tree structure, that actions have unique names, and so on. Now, GOLOG is a language that allows us to express complex actions, also called programs, over the primitive action defined in the basic action theory. Its semantics is defined using the do predicate with a capital D that intuitively is used to express that there is a successful execution of program delta leading from situation S to S prime. Do is defined inductively by means of a macro. Here we consider the most basic set of program constructs containing primitive action, test condition, sequence, non-deterministic branching, non-deterministic choice, also called pick operator, and the Kleene star. Planning our program execution then boils down to a reasoning problem where we try to prove the existence of a situation S that is reachable from S0 by means of an action sequence admitted by program delta. Also notice that due to non-determinism in general, the same program may admit multiple execution sequences. First, let's briefly talk about some extensions to the standard situation calculus. One thing we want to be able to handle are what we call aspects, which are typically expressed through adverbials in natural language. For example, when we have a statement such as the robot closes the door gently, because we only considered a single agent case, the agent would not be represented explicitly. The verb or predicate of the statement would correspond to the name of the action, and the object would be an argument of that action. But what about aspects? Of course, we could simply represent them as arguments as well, but this would have the drawback that we would need a large number of them, in particular if we want to be able to represent arbitrary combinations of them. Instead, we propose to extend the syntax of actions so that they take finite sets of the explicitly mentioned aspects as their last argument. And formally, these finite sets are represented by means of reification, and an action with aspects just stands for a GOLOG expression that makes use of the pick operator and a test condition. In this fashion, we can represent actions with multiple aspects, no aspects, and also negative aspects, meaning a corresponding aspect is absent. This nicely captures the intuition that an action with more aspects in terms of set inclusion is more specific than an action with fewer aspects. So for example, closing the door gently is more specific than just closing the door. We also extend the GOLOG language by two additional constructs. First, we define the joint execution of two programs simply by means of taking the conjunction of the do expressions for the two subprograms. For example, jointly doing walk or sing, and sing or talk only admits sing. And so basically you can think of this operator as the intersection of the two programs. And this should not be confused with concurrent execution. We also need a notion of refraining from doing certain actions. Similar to the above, we may be tempted to just take the negation of do delta as prime here, but this would have the undesired effect that otherwise unreachable situations would suddenly become connected. And it turns out that the definition of action negation is an issue in and of itself and far from trivial. In the paper, we have a bit of a discussion on the issue, but long story short is that here, for the sake of simplicity, and because it is completely sufficient for what we're doing, we restrict action negation to programs which only ever admit single actions. This leads to the following definition. A guarded action is a primitive action preceded by a sequence of pick operators and test conditions. A special case of this are the aforementioned actions with aspects. The guarded action fragment then is the set of all Boolean combinations of such guarded actions. In particular, this includes the universal or wildcard action, note that situation calculus allows to quantify over actions, denoted by top, and the failure action denoted by bottom. Not too much of a surprise, we get that the guarded action fragment is a Boolean algebra. Also, the GOLOG fragment with non-deterministic choice sequence and Kleene star is unsurprisingly a Kleene algebra. But what this tells us is that we can essentially just apply the usual laws and rewriting rules for these algebras to our programs. The goal for our main framework is to define a preference relation over situations, intuitively saying that a situation S is deontically more ideal than another situation S prime. We can then define the minimal situation sigma prime reachable from sigma by means of program delta, which are simply the ones reachable as defined through do, such that no other more ideal situations are reachable. This gives us derived notions of dyadic obligation and permission, where these operations should be read as gamma is obligatory or permissible, given that the agent is committed to a course of action according to delta. Note that here we deviate from the usual KD-style definition of these concepts, namely we view obligation as representing all and only ideal situations, and this lets us avoid another paradox of Deontic logic, namely the unintuitive case where the obligation to mail a letter entails the obligation to mail it or burn it. Similarly, permission here is not the dual of obligation, but a variant of strong permission, which has the effect that non-determinism indeed encodes a free choice for the agent, and that the permission for choosing between gamma 1 or gamma 2 is the same as having both the permission for gamma 1 and gamma 2. To obtain such a deontic preference relation, we now propose to employ conditional rules over expressions from the guarded action fragment. Such a rule should be read as if the agent is committed to a course of action admitted by delta, then it ought to do gamma. Defining the exact semantics for a set of such defeasible conditionals is an issue in and of itself, and there has been lots of work on this subject. Here again, for simplicity and because of the nice computational properties, we choose a semantics akin to Lehman and Majidor's rational closure. If you're familiar with rational closure, the following will look, very familiar. The difference is that instead of propositional formulas, we apply conditionals to complex actions, and consequently, instead of possible worlds, they refer to situations, and the notion of consistency is replaced by reachability. First, because we have action negation, we can define the materialized version of a conditional, and with a new joint action operator, we can say that the materialization of a set of rules is simply the conjunction of the individual rules. And furthermore, we define exceptionality of a rule with respect to a set of rules to mean that the antecedent of the rule is not jointly executable with the materialization of the set. A set of rules then induces a ranking where rank 0 consists of the overall set of rules, and every higher rank consists of the rules that are exceptional at the previous rank, and the rank of the situation sigma prime from the point of view of another situation sigma then is simply the minimal rank that lets us reach that situation. Let's look at the Forrester scenario as an example where the agent generally ought not move the base, but if it does, it should do so gently. First, we have the materialization of the two rules according to the definition that we just saw. We can simplify the expression using Boolean algebra. Apply the distributive law, simplify a bit more, and note that G is a more specific version of M, so not M and G are not jointly executable, and so the whole expression reduces to not M. We can then see that only the second rule is exceptional, as its antecedent is obviously incompatible with not M. So the next rank only contains R2. the rule is not exceptional with respect to itself, and so at rank 2 we already end up with the empty set. The resulting ranking correctly assigns 0 to all actions distinct from moving the vase. Moving it gently has rank 1 and moving it non-gently has rank 2, so this example works out nicely. In addition to what we just saw, we also consider temporal action conditionals. Here we have two different styles of rules. One to express that if committed to do delta, the agent ought to do gamma afterwards, and similar for before. We have to adapt the notions of materialization and exceptionality accordingly, and now taking into consideration that rules talk about sequences of two actions, and depending on which style of rule is being used, the antecedent refers to the first action and the consequence to the second, or vice versa. Again, let's look at an example, namely the aforementioned chisel paradox. We ought to go help afterwards, and if we go help, we should tell, and if we don't go to help, we shouldn't tell. And for rank 0, we again have to determine the product of the materialized versions of all three rules. The one for rule 1 can be simplified, the one for rule 2 is this, and the one for rule 3 can also be slightly simplified. Again, we can apply the distributive law to multiply out these expressions, giving 4 combinations, but notice that these two and these two are not jointly executable, so we end up with this, which can be further reduced to T sequence H. Now only rule 3 is exceptional, since we cannot execute top not H jointly with TH, so that's what we obtain for rank 1. And rank 2 is given by the empty set. And the resulting ranking assigns 0 to first telling and helping, 1 to anything followed by not telling, and 2 if we first tell we're coming and then actually don't show up to help. And once again, this example works out nicely. Finally, we need to define our overall preference relation from these rankings that we computed. Here we use a perhaps overly simple additive model, mainly to keep things simple, where the general D rank of a situation is given by the sum of all ranks assigned from any preceding situation to any other preceding situation. Sigma is then preferred over sigma prime if sigma's D rank is lower. Another contribution in the paper is a compilation approach. Here the idea is to incorporate the ranking information given by the set of Deontic rules directly into the basic action theory so that we can make use of the usual reasoning procedures for situation calculus. For this purpose, we introduce a numeric ideality fluent that is assigned value 0 in the initial situation and which has a successor state axiom where its value is increased by a certain non-negative badness value associated with the action being executed. We pre-compute the ranking, which we can do when making the sufficient assumption that rankings are situation independent, and we always have complete information to decide whether a rule is exceptional. We can guarantee this to be the case, for example, when all guarded actions involved are actions with aspects, just like in the examples that we've seen. We then define a compilation operator that expresses that an action A is a possible execution of delta in situation S in terms of a formula uniform in S. Please refer to the paper for details, but if you're familiar with the regression operator for situation calculus, this works very similarly. This may sound more complicated than it is, but for example, in the Forrester example, this would be the definition of the badness value, which is more or less just the ranking that we just saw before, slightly rewritten as an axiom. In the temporal case, we have to consider sequences of two actions, gamma and delta. To again get axioms of the right form, we use the idea to introduce finitely many additional fluents in order to memorize whether a corresponding gamma has just been executed. Initially, these fluents are set to false, and for their successor state axiom, we can just apply the previously shown compilation operator. The badness axiom for the chisel scenario then looks like this, where badness 0 is assigned to action A in situation S if tell was executed previously, and A is action help, and so on. As a theorem, we get that our meta-theoretic definition of D ranks coincides with the value the ideality fluent takes according to the new basic action theory. To conclude, we presented an approach to represent contrary to duty constraints over complex situation calculus actions in a non-temporal and a temporal variant. We also showed an approach to compile the corresponding information directly into the basic action theory. For future work, we want to look at adapting other kinds of conditional systems. In particular, in this talk tomorrow, Jim will show an approach that, among other things, handles specificity better than what we presented here. Another important direction is to consider larger fragments of GOLOG for specifying constraints, in particular with regards to including iteration. And finally, we are in the process of implementing and evaluating the approach. Thank you for your attention, and I look forward to your questions.